I'm going to talk about how I'm using FME in my dynamic flood calculations. I've been developing some tools that I use for processing input data that I need, but also to process the results that I get from my flood calculations. So first of all, I work at the company, engineering consultancy company that originates from Denmark. We are around 10,000 employees. We are most active in Denmark, Sweden, Finland, and the United Kingdom. We have around 200 offices in 20 different countries. You can see that's our main office in Copenhagen. The outside, and that's the inside. And if you have been to Copenhagen, you might have seen the Bella Sky Hotel, which is quite spectacular. We have been designing that. It's two buildings. First of all, it's the lower part is leaning towards each other, and then the upper part is leaning away from each other. So there's some very advanced calculations made on that. Unfortunately, not with FME, but I've also been involved with the Femern Belt tunnel, which is a tunnel between Denmark and Germany. It's 18 kilometers long, and I've been designing the stormwater retention basins, but they are designed with FME, of course. So in 2020 or 2025, you can look on Google Earth and see all the basins if you want. Yeah, I'm Swedish myself, but I work in Denmark, so I use this beautiful bridge that we made between Sweden and Denmark every day. And you don't need to have a passport or anything when you travel around in between Sweden and Denmark, and not in the European Union countries. So that's really convenient. I work in a department that work with climate adaptation and stormwater management as their main tasks or main projects. My mainly work is to do dynamic flood mapping with DHI software from the Danish Hydrological Institution. I work with Mike Urban, Mike 11, and Mike 21, which are developed by DHI. Mike Urban is used to model a drinking water system and also sewer systems. Mike 11 is to model river systems, and Mike 21 is to model overland terrain flow, or you can use it also to model lakes and the sea, everything. And the good thing is that you can couple these models two-way or three-way. You can choose yourself. That's actually really convenient and works really good. I have at least 5 years experience in two-way coupling and about 1 year in three-way coupling, but the three-way is really interesting and good. Yeah, I have a lot of experience in FME and ArcGIS. I don't tend to use it as much. I want to use it more, but I use it maybe 10% of my day. Currently, I'm working on a project in Gothenburg where we are building up a hydro model to make flood calculations for future scenarios in Gothenburg. So what I'm going to talk about today is, first of all, how I manipulate DTMs that I use for input to the Mike 21 model, and also how I post-process my flood results afterwards to get some statistics out of it. Most of you might know that the DTM is the terrain level where we have cut away houses and trees and everything that you don't want. You only have the terrain left. But when you do flood calculations, houses are actually obstacles for the water when it flows underground. So we want the water to flow around the buildings. So we have to reverse that process and build the buildings into the DTM again by just raising the cells where you have houses. Yeah, so this is what I have here on my left hand. I have the DTM without houses. And then I've added the shape files of the houses. And then afterwards, you can see the result when I've raised the terrain for where there really are buildings. Yeah, so my principal solution is that I have a raster, I have some shapes. So first of all, I use a clipper to clip the houses out, and then I have the outside that I don't want to change. I want it to be as it was in the input raster. I've done this actually some different times and used some different techniques. This is the quickest one that I've found. The first thing I did was to convert that raster results to points, and then just changing the set value and then interpolating it back to a DTM. That works fine, it's a good method, but if you're using a very large raster, it takes a lot of time to do it. So I was very happy when I found the raster cell replacer and the raster cell value calculator. So I actually found a method. If you take these smaller ones and just set them to a value 5, whatever I want the building to be raised with, and then so I have the original values here, and here I only have the number 5 in each cell. And I take those, put them into the raster cell value calculator, and in there you can choose different operands, minus, plus, multiply, or division. I just choose the operator plus, so I get the DTM value plus 5 meters. And then I just take simply the output from the clipper and mosaic that back with the raster mosaicer, and take the DTM plus 5. And then I get my raster back, and I've only changed the cells that I really want. This is the FME solution of it. First of all, I just read in some shapes, and I'll run it through a geometry filter just to make sure that it's only area files that I'm getting. This makes it possible to read from an AutoCAD file or a MapInfo file or whatever that can contain several different types of features. I found it best to aggregate these buildings or shapes that I read in. Otherwise it don't work. I can't remember why it didn't work, but you had to aggregate it. And then I clip it, and then I do this solution here where I change the value to 5, and then clip it back with the inside not changed or unchanged DTM values. Just add the 5 meters and then take the output here, mosaic that to back again, and then I set a custom file name that I have entered as a parameter. And then I save it back to any type of raster format. So that was the first one. The second one is after I've used that DTM now to make some flood calculations where I have both the sewer system and a DTM. So it works like this. If you have some rain that goes into the model, and then that's all the sewer pipes get filled up because you have too much rain coming into it, and then it surcharge or get pressed up to the streets, and the 2D model calculates how the water is flowing. So this is results here. So I've had some flooding here in the streets, and because we have some low-lying terrain here, the water can travel in between the houses and out, and it soon finds a deep point here where it's collected. And this here is actually a river that goes through. So what I want to do with this is I want to know how big area is flooded and with how much water is it flooded with. And the technique I'm using gives me a bonus, and that is I can get all these individual flood islands. I can get the flooded area and volume for all of those as a shapefile that I can use. But I can also summarize it so I only get the total results. And also a plus with the group by function is that I can take results from 10 different scenarios, run it through the same workspace and it analyzes it individually. So the solution again is that I have some flood raster results where I only, instead of having a lot of values, I only have a value where it's flooded and everything else is just no data values. And my output is a Excel statistical file with all the statistics and a shape file where I can click on each individual island and find the flooded volume in the different areas. And I've also done this in several different solutions that were much slower. The first version I had to, instead of using this raster extent cursor, I had to take all the points, make a buffer, and dissolve that together to find out which flood cells that were connected to each other. But instead of using this raster extent cursor, which is very quick transformer, it's per default used just to find the outer boundaries of a raster. But if you go into it and set it to data extents, you get polygons only for the areas where you have some type of value, and the no data values are just left as they are. And I can imagine that you could have some type of a threshold. If you say everything beneath 2 centimeters of water, that's nothing I want to look at. That's okay flooding. You can just take the values and reduce it, and then you would also get a slightly smaller data extent area. So I take my flood results. I first of all convert it to points, and then I get the flood depth in each point, and also the coordinates of it. And then I run it through the raster extent cursor to get the different individual flood islands. And then I use a point on area overlayer, and that one gives me a count of how many hits it had, how many cells that were inside this polygon. And by knowing the size of each individual cell, you can just multiply that area and then you get the total area. And you do the same with the volume. You calculate the volume for one and then summarize them. And then also I get a list for all the points. And for the list, there are a statistical calculator, but it calculates statistics based on different features. So you could argue that you could take this list and explode it and then calculate some statistics on it. But I think it's quicker to do it with the Python caller, because there are some built-in functions in Python to do some statistical analysis of lists, and I also think it's more fun to do it in Python, so I've done it in Python. Yeah, so I use these two, Python caller and the attributes creator, to create the attributes I need to represent the total flooded area and the volume, and the volume of the flooded water. And then I just take this and export that as a shapefile, and I export it as an Excel file. So the FME workspace, first of all, I take the flood result and clip it with some type of a boundary. It could be that you have a very large flood model and you're only interested in a small area. Typically, we work for municipalities, and they are definitely not interested in water that's outside the municipality boundary. So we cut the boundary for the municipality. So up here, I just convert it to points and just rearrange the set attributes. I extract the properties here. You can, with the raster property extractor, I think it's called, you can get the space in X. So it makes it dynamic. Normally we use the same type of spacing, but sometimes we use 1.6 meter and 3.2. So this makes me independent, so I don't have to think about the size, and it takes care of it automatically. yeah, and then it's really this one that makes the job, making all those small flood islands, and it actually gives it as aggregated shapefiles. I have to run a deaggregator to get all the individual flood islands as one feature. And then take the points and overlay those in the area. And I get the list and the count out from that. And then in the Python caller and attribute creator, I just calculate the average, maximum, and flood, and also the flooded area and volume of the flooded water. And then first of all, I just output it as shapefiles, and then I aggregate it together to get the total amount of flooded area and volume of flooded water. So here on the left, you can see an example from ArcMap, where I've added the shapefile. So if you click on one of them, I can get the total number of cells that was in that island. It's 2,000 square meters that's flooded, and with 232 cubic meters of water. The average depth was 11 centimeter, and the maximum depth was 30 centimeters. And you could use that to map it out, to see which islands that are very deep and which ones are very shallow. I've done that sometimes. But mostly I tend just to represent it actually as a diagram. Here is a snippet of the Excel file where I have the file name of the flood results, the number of cells that were flooded, the area that was flooded, and the volume. And typically when we do flood calculation, we do it for different scenarios. And here we can show the customers here at these scenarios here gave really big flooded areas, but if we do some solutions, establish some pumping stations or bigger pipes, we can come down to a lower flood value. So it's quite illustrative to do it. And it's very quick. Before you had to do it each and every time for each result, but now I can automate it, everything together. That was the last slide. So do you have some questions?
Thank you. So, does anybody have any questions? It was definitely interesting to see the suggestions how to do something better, one way other than another way, and the remark about being able to do something fast and easy now, when before it was much more complicated process. It's really,
I've been using it for 4 years, I think, at least, and I've remade it 2-3 times at least. So I really, I got more efficient by finding these extra transformers that did it much more efficient and much quicker for me.
Yeah, and it's kind of research type of work.
Yeah.
Please go ahead.
Yeah, I know you use the mic software to actually do the flood calculation. Do you see an opportunity to incorporate more of those kind of calculations into FME itself?
The flood calculations, you mean?
Yeah.
The problem is that it's much very advanced calculations that is taking place, and you have some types of calculations that you make in the pipes, and then some other types of calculations on the surface. And yeah, there's many things. You have to have the resistance and everything. There are some default values for that, but it's quite complicated calculations to do, unfortunately. But I'm thinking a little bit about automating maybe simulations to have like an online model that you tell it to run for a specific time, and then you have some automated scripts that present some results of it. So you could have a service that takes in rain data, and then you present some flooding results. It could especially be interested in when you have these individual flood events. So you can see, you get a map of what's the model saying that you had as a flooding. But sometimes it's unfortunately not the same as the reality, but you get a hint of where it's flooded. I worked for a water and sewer utility company before, and when you're sitting there, you get all those reports about people having flood in their basements and everything. But you know that there are often some old people that just accepted it. It has been that for the last 20 years. So you don't get the reports from them, but the model can really show you where you have the largest risks, even if you don't get a report about flooding.
With the raster properties extractor, what is it you do with the data after that? Can you flip back to the workspace perhaps? And,
Here. Oh,
that was it, yeah.
here, yeah.
Yes.
So actually, this one is just used to find the spacing of
Okay.
in X.
Okay, so what is there anything you do with that spacing number in the
I use
workspace?
that to calculate the area of the individual cell.
Okay.
So if the cell size is 2 meters, I take
Okay.
2 times 2.
Okay.
And if I have a result where, yes, I could actually give it 2 different results with 2 different types of
Okay.
grid cells. And
So that way,
yeah,
I guess you can handle any size of data that comes in.
yeah, as long as it's
Okay.
raster
Yeah.
data.
Okay.
Yeah.
Any more questions?